In the previous class, we studied algebraic rules for limits. Now we will explore algebraic rules that apply to continuous functions. Since continuity at a point depends on the limit of the function at that point, we can anticipate similar results analogous to the case of limits. Let us learn the algebra of continuous functions. Suppose f and g are two real functions continuous at a real number c. Then, first, f plus g is continuous at x equal to c. Second, f minus g is continuous at x equal to c. Third, f times g is continuous at x equal to c. And fourth, f upon g is continuous at x equal to c, provided g of c is not equal to 0. Let's prove these results one by one. Consider the first case. Continuity of f plus g at x equals c. Since f and g are continuous, limit x tends to c f of x exists, and same with the g of x. Now using the limit of sum property, we can write limit x tends to c f of x plus limit x tends to c g of x is equal to limit x tends to c f plus g of x. Hence, by the definition of continuity, we must say that f plus g is continuous. In a similar way, we can prove f minus g and f times g are continuous at x equals c as follows. And similarly, f upon g is continuous at x equals c, provided g of c is not equal to 0 as. So we understand the proof. Let's learn the two special cases when f of x is a constant function. Case 1. Case 2. If you observe case 1, when lambda equals -1, the continuity of g implies the continuity of negative g. And in case 2, when lambda equals 1, the continuity of g implies the continuity of 1 upon g. So, we have learned the concept. Let's apply it to a problem. Discuss the continuity of the following functions. First, sin x times cosine x. Second, sin x upon cosine x, where x is not equal to 2n plus 1 times pi by 2 and n belongs to integer. First, sin x times cosine x. Let f of x equal sin x and g of x equal cosine x, defined for all real values of x. Since sine and cosine are continuous functions, using the theorem that f times g is continuous at x equal to c if f and g are continuous functions, we can say that limit x tends to c f of x times limit x tends to c g of x is equal to limit x tends to c sin x times limit x tends to c cosine x, which further equals limit x tends to c sin x times cosine x. On simplifying, we get sin c times cosine c equals f times g of c. Thus, we can say that the given function is also continuous. Second, sin x upon cosine x, where x is not equal to 2n plus 1 times pi by 2 and n belongs to integer. Let f of x equal to sin x and g of x equal to cosine x, defined for x not equal to 2n plus 1 times pi by 2 and n belongs to integer. Since sine and cosine are continuous functions, using the theorem that f upon g is continuous at x equal to c, provided g of c is not equal to 0, we can say that limit x tends to c f of x upon limit x tends to c g of x is equal limit x tends to c sin x upon limit x tends to c cosine x equals limit x tends to c sin x upon cosine x. That is further equal to sin c upon cosine c, or f upon g of c. Thus, we can say that the given function is also continuous. Since we learned the algebra of continuous functions, let us discuss an interesting fact in the behavior of continuous functions with respect to the composition of functions. Suppose f and g are real-valued functions such that f of g of x is defined at c. If g is continuous at c and f is continuous at g of c, then f of g of x is continuous at c. Let's solve an example to understand it better. Show that the function f of x equal to sine x squared is a continuous function. We know that f of x is defined for all real numbers, and it is the composition of two functions g of x and h of x. F of x is equal to g of h of x, where g of x is equal to sine x and h of x is equal to x squared. Since both functions are continuous, by the theorem of continuity of composite functions, we can say that f of x is also continuous.
Let's summarize what we have learned.